Welcome, future pharmacists, to today's Explainer. Let's kick things off with a pretty fundamental question. What happens to a patient's cells if their blood just stops flowing? It's a dire scenario, right? And as clinical professionals, understanding exactly why it's so critical is the absolute cornerstone of patient care. So today, we're diving into a clinical masterclass on the very river of life flowing through our veins. Here is the agenda for today's Explainer. We'll cover 1. Intro to hematopoiesis, 2. Clinical profile, 3. Physiological functions, 4. Composition breakdown, and finally, 5. Clinical terminology.
All right, Section 1, Intro to Hematopoiesis.
So if we break that word down, hemo refers to blood, and poiesis means formation. This physiological process of blood formation is literally the foundation of human health. Without hemopoiesis, the body simply cannot sustain itself, period. Now, clinically speaking, blood isn't just a liquid. It's officially classified as a specialized fluid connective tissue. Think of it like a highly efficient, high-speed highway. It delivers vital oxygen and digested nutrients, stuff like glucose and amino acids, directly to every single cell in the body. And at the exact same time, it hauls away toxic carbon dioxide to the lungs and waste products straight to the kidneys. If this fluid highway gets blocked, the cells are starved and they suffocate. Moving right along to Section 2, Clinical Profile. First up, let's talk volume. An average human holds about 5 to 6 liters of total blood volume. To put that into a practical clinical perspective, for an individual patient, blood accounts for exactly 8% of a person's total body weight. So if a patient is heavier, their blood volume is going to be correspondingly higher. Now, this is actually pretty wild. We all know normal human body temperature sits around 37 degrees Celsius, right? Well, blood actually sits at a toasty 38 degrees. This is because of the constant dynamic friction created as it's relentlessly pumped by the heart and forced through thousands of miles of blood vessels. Next, we have viscosity. Blood is significantly thicker, more viscous, and slightly heavier than plain water. In fact, it flows with 4.5 to 5.5 times more resistance than water. And that thickness, it's incredibly important for maintaining a patient's blood pressure. Okay, this point is absolutely crucial. The pH. Blood sits slightly alkaline at roughly 7.4. It's not neutral and it's certainly not acidic. It acts as an essential chemical buffer. If this number swings too far in either direction, your patient's acid-base balance is completely wrecked, leading to immediate systemic emergencies. Section 3, Physiological Functions. So what is all this viscous, slightly alkaline, 38-degree fluid actually doing in the body? Well, it's the ultimate multitasker. We've got 9 pillars of physiological function here. Blood transports gases and nutrients. It balances ions and water. It regulates our internal thermometer. Your white blood cells act as the body's defense soldiers, actively hunting down foreign pathogens. Plus, it's the primary vehicle for excretion, carrying nitrogenous wastes like urea and creatinine straight to the liver and kidneys. Let's zoom in on just one of those critical functions: coagulation. When a vessel is cut, specialized components called thrombocytes, which you probably know as platelets, rush to the scene. They trigger a rapid cascade that forms a vital fibrin plug. It's essentially like throwing a biochemical net over the injuries so the patient doesn't continuously bleed out. Let's get into the nitty-gritty. Section 4, Composition Breakdown. If you grab a vial of blood and spin it in a centrifuge, it separates beautifully into 2 main layers. The pale, yellowish fluid on top, that's the plasma, makes up 55% of the volume. The solid, heavier cells, known as the formed elements, settle at the bottom and make up the remaining 45%. Let's look at that 55% pale yellow plasma first. It's overwhelmingly composed of water, about 90 to 95% actually. This water acts as the grand transit system. It dissolves and carries amino acids to build proteins, circulates hormones to their target tissues, and sweeps away liver-produced wastes like urea and uric acid. But here's a crucial detail. Plasma also holds about 2 to 3% proteins, almost all of them produced by the liver. The breakdown here is key. Fibrinogen handles the clotting we just talked about. Globulin acts as the basis for your immune system's antibodies. And the most abundant by far, taking up 60% of that protein space, is albumin. Albumin is what prevents blood from leaking out of the vessels by maintaining a precise osmotic pressure of 25 millimeters of mercury. Now, for your future clinical lab tests, you have to lock this definition in. You're going to hear the term serum all the time. If you take plasma and purposefully remove fibrinogen and all the clotting factors, the fluid you're left with is called serum.
It's a really critical distinction when you're ordering and reading blood panels on the ward.
All right, sinking down to the 45% of blood, that's solid. The formed elements. Ordered by their relative abundance, we start with erythrocytes, or red blood cells. These carry hemoglobin and have a 120-day lifespan. Next up are the thrombocytes, or platelets, for clotting. And finally, the least abundant but highly critical, leukocytes, or white blood cells, the soldiers of the immune system. Now, those leukocytes are categorized in a very specific way. Here's a quick memory trick for your exams. Granulocytes have a tiny, bumpy, granular surface. Basically, if you could touch them, you'd feel the bumps. Because of that, their names all end in -phil, neutrophil, basophil, eosinophil. On the flip side, agranulocytes lack those granules entirely, which covers your lymphocytes and monocytes. Let's bring this all together into Section 5, Clinical Terminology. You're definitely going to want to mentally bookmark these clinical ranges. They show the exact normal baselines per cubic millimeter, and the critical terminology for when those counts dangerously shift. Notice a pattern here? The suffix penia generally means a dangerous drop in count, like leukocytopenia or thrombocytopenia. An abnormal increase in red blood cells is polycythemia, while a drop is the widely known anemia. For example, let's look closely at the white blood cells. A normal count is between 4 and 11,000. Notice how a massive abnormal spike in leukocytes, far beyond that 11,000 limit, leads to leukemia. The body is essentially overproducing white blood cells, which is exactly why leukemia is known as such a devastating form of blood cancer. So, we've thoroughly mapped the river of life today, from its chemical composition all the way down to the exact terminology that dictates a patient's diagnosis. But I'm going to leave you with this. Having memorized these numbers, how will you actually apply this foundational blueprint to save lives when a patient walks into your ward presenting with a sudden, severe case of dengue-induced thrombocytopenia? Think critically about what systems would fail and exactly how you'd intervene. Until next time, keep learning and keep explaining.